Last time we were talking about really sort of some basic, for the most part, they're kind of conversion factors. We talked about a couple important units and stuff like that, really grams and moles. And also we talked about Avogadro's number, I believe last time as well. So it's just kind of, again, review some of that stuff there. So the first thing we started talked about was really the conversion to go from, say, moles to either atoms or molecules, which are kind of two conversions, and either that way or to go the opposite way from atoms back to moles, again, or molecules. And we really use Avogadro's number to do that conversion. And Avogadro's number is that 6.022 times 10 to 23. Remember that when we use Avogadro's number, the units really, for the most part, could be anything you want. And that's basically equal to 1 mole. And usually atoms or molecules or, usually the units that we use um, with Avogadro's number. But again, technically speaking, you can kind of use any units that you want. Remember, Avogadro's number really going to use most of the time as a conversion factor, and since it is kind of like a conversion factor, you really can use it, sort of both ways in dimensional analysis. You can have Avogadro's number up on top and 1 mole on the bottom, and this would be a case where you would be, for example, starting with moles, and you basically would multiply the moles times that conversion factor, and that obviously would give you atoms or molecules, again, if you're kind of dealing with molecules. Alternative to that, again, if you kind of start with either kind of atoms or molecules, um, you could use Avogadro's number sort of as the opposite way here in dimensional analysis and as a conversion factor, which basically is just dividing by Avogadro's number. We could put that on the bottom, moles up on top. Again, atoms would cancel, and that would give you moles. So again, this is sort of where we want to use Avogadro's number in a case where, we're going from moles to atoms, and again, our molecules are going opposite way. Remember that we don't want to kind of use Avogadro's number in every single calculation that we do. The key word there is really the words that we see there on the right, which is in the problem. There should be a mention of atoms. There should be a mention of molecules or something like that. And then you need to use Avogadro's number again, usually to get to that mole sort of situation. As we talked about last time, if there's really no mention of really any atoms or molecules in the actual problem, then you really shouldn't be using Avogadro's number. Um, in good situations, a badly used Avogadro's number, people will multiply by Avogadro's number in the front of the calculation and then come back and divide it out at the end. In bad situations, they don't kind of divide it out at the end, and you will get the wrong answer. So the key there is to make sure that the problem somewhere along the way does sort of mention those words. Also, a key reminder that when you do see MOL here, that is for moles, again, not molecules. So that's another very common sort of mistake that people make, is they see sort of the abbreviation for moles and they automatically think molecules. So again, that MOL is the abbreviation for moles. It doesn't really stand for molecules. The other really important sort of really conversion factor sort of that we used or talked about last time was molar mass. And molar mass is really taken from the periodic table. It really comes from the number that's on the bottom. And if you remember, the number at the bottom really is the atomic mass in AMU per atom, as we talked about. And we also talked about last time how to calculate the atomic mass, which is to take the percent abundance of each of the isotopes and times them by their atomic mass and add them together. Um, but numerically speaking, molar mass, which is sort of grams per mole, is numerically equal to really the AMU per atom, which means we could also look at that bottom number, even though correctly speaking, it is atomic mass, as sort of the molar mass for that particular element. And that would basically tell us how many grams there are per mole. So the molar mass of hydrogen would be 1.008 grams per mole. The number always goes with the grams part. And again, as we talked about, I think at the end last time as well, when we do calculate molar mass, it always is 1 mole. And that what that basically means is we want to go based off of the formula, add up all the parts to the formula, and that will give us the molar mass again in grams per mole. We really could think of molar mass also as a conversion factor, grams and moles. You could use it as grams on top, moles on bottom, or moles on top and grams on the bottom. And again, it is our conversion factor really to do one that we do a lot in chemistry, right? Is going from grams to moles and backwards, basically. So in this situation, if you were starting with grams, you would use the molar mass really in a dimensional analysis way by putting the grams on the bottom, the moles up on top, basically dividing by the molar mass would give you moles. If you started with moles and wanted grams, we basically use the molar mass, again, dimensional analysis way, grams up on top, moles on the bottom. Moles would cancel and it gives us grams. We could get the molar mass for a particular element. If we have a molecule or something like that, we basically could add up all the parts of it, and that would be 2 times 1.008 grams per mole plus 16 grams per mole. Again, I'm getting these numbers from the periodic table there, and 1802 or something like that. Grams per mole would be the molar mass of water. Again, if we were using Avogadro's number with something like water, we would use the units of molecules. So sometimes these are sort of put together, are used together in that sense. Again, we could say there's 18.02 grams of water, basically in 1 mole of water. And in 1 mole water, there is basically 6.022 times 10 to the 23. Again, these would be molecules, because we're dealing with water here, of water. Any questions on any of those sort of stuff that we talked about? I think last time, again, we did have that other major thing, I guess, we sort of talked about was the atomic mass, and that the numbers that we see up there on the periodic table are average atomic masses of our naturally occurring isotopes. And remember, for that guy, we do our atomic mass is the percent of the isotope times the atomic mass of the isotope plus the percent of the other isotope times the atomic mass of the second isotope. And again, if you had 3 or more, you kind of continue that pattern. So that is, again, how we sort of come up with those numbers that we see on the periodic table. Any questions on any of that stuff I think we covered last time there? Okay. So I think we kind of left off into some of these examples here of grams, moles, and everything like that. So why don't you give this a go and see what you come up with. What is the molar mass of 1 gold atom? These are some of the numbers there from the periodic table. Molar mass of gold is 197 grams per mole. So see what you come up with, and we'll talk about it. Okay, so let's take a look here and see how we're doing. We want to know what is the mass in grams of 1 gold atom. So a couple of keywords as we sort of been talking about. Clearly here I see the word atom, which means I do need to use Avogadro's number somewhere. So again, as it shows up there, that basically means 1 mole is our 6.022 times 10 to the 23 atoms. In order to use Avogadro's number, I really need it in moles, and I'm starting with how many grams there are. I'm looking for how many grams there are. So that means that we do need to go from atoms to moles, and then moles to grams. So we're starting with an atom, and that's going to take us from atoms to moles, and then from moles we could go to grams, and that is our molar mass to do that. So that's basically what we're starting with, is just one old gold atom there. So that's what we will start with, one gold atom. Again, we're going to go from atoms to moles here using Avogadro's number as a conversion factor. Again, doing a dimensional analysis way, putting our Avogadro's number in this case on the bottom so that the atoms cancel and moles up on top. If I stop the calculation right at this point, the atoms would divide out. We would be left with moles, which is close to where we want to get to, but we do want to get to grams. So that is where we're going to use our moles now to go to grams and our molar mass. In this case, we could just go to the periodic table and we see that the molar mass of gold is 197. And again, that basically means 197 grams per mole. You could get an answer at this point, or you could continue on. I'm going to continue on here. And again, remembering dimensional analysis way here, I got moles up on top, opposites cancel. That means that we do need moles on the bottom and the 197 grams up on top. The moles here will then cancel. That leaves us just grams up on top, which is good, which is what we're looking for. A reminder that we're basically just multiplying across the top there. So that's basically 1 times 197 can hit equals. We're then dividing by the bottom. We're going to divide by 6.022. Make sure you use your exponent button, and 23. I personally will hit equals at this point. And obviously the last number there is 1. You don't really need to divide it out. You can obviously if you want to. And if we do all that good stuff, we do end up with about 3.271 times 10 to the minus 22 grams. That obviously is a super small number, which is, makes sense if we think about, we're talking about one individual sort of gold atom. And obviously it should be a very, very small number, as atoms are very, very small. Question on any of that calculation there? Now you may be wondering why I went to 4 significant figures on this one, and it's because technically speaking, if we had one gold atom, even though we wouldn't be able to see it with our obviously naked eye or something like that, it would be more of an exact number. You would probably just count it. And that means because it's an exact number, they pretty much can have as many significant figures as you want. So here I just went to 4, like the molar mass and all that kind of guys. We're at 4 significant figures. Any questions on any part of that calculation there? Okay. So again, the key there is you want to make sure, if what you are looking for involves anything that involves atoms, molecules, or something like that, again, you do want to use Avogadro's number somewhere along the way. Now let's take a little look at this problem here together. It's a little bit different than some of the problems that we've done before here, and let's see how it's sort of different and some ways that we can sort of figure out this type of problem. Here we're looking for how many hydrogen atoms there are in 72.5 grams of C3H8O. So a couple important things. Obviously, we see something about atoms. So probably Avogadro's number there is in play. So obviously, again, Avogadro's number. But the really important thing is we are actually looking for just the hydrogen atoms by itself here, and not the entire thing. So if we look at the formula here for this compound, it contains carbons, it contains hydrogens, it contains oxygens. In this particular problem, though, we're actually only interested really in the hydrogen part of it. So somewhere along the way in this calculation, we need to go from this entire thing to really just the hydrogen part of it. So what's going to allow us to do that is a couple of things to think about. We do need to get to sort of atoms. We are starting with grams, right? So kind of our grams to moles to atoms is sort of the process we're going to go. So obviously this is molar mass to do this. This is Avogadro's number. But there is a key in the middle here where we got to get to just hydrogen and not the entire thing. So we can actually use in this case and in problems like this, the actual chemical formula to sort of help us do that. And I think we just touched upon it last week. When we look at these sort of subscripts here on the bottom, one way you could kind of look at these subscripts is how many moles there are of each of those sort of elements. And what that allows us to do is we actually can use the formula itself as conversion factors. And what I could say is, for example, in 1 mole of that entire thing, that's C3H8O, there would be 3 moles of carbon. And again, I would get the 3 from here. I could also say that in 1 mole of that entire thing, there would be 8 moles of hydrogen. Again, the 8 would come obviously from here. And in 1 mole of the entire thing, there would be 1 mole of oxygen. So from the actual chemical formula, we actually can come up with, as you can see, 3 equalities and 3 really conversion factors that allows us to go from the entire compound to each of the individual elements. Any questions on that there? So obviously in this particular problem, we're interested in just the hydrogen part, which means we are going to use basically this conversion here to go from the whole thing to just the hydrogen part. Now, in order to use this relationship, this is a mole to mole relationship, which means in terms of the whole thing, I do need to get it into moles, which means I'm in grams right now. So I do need to do kind of a conversion factor like we've been doing, basically take our grams into moles. So to do that, I need the molar mass of the entire compound here. So that would be really the first thing that we'd want to calculate is the molar mass of the whole thing. And if we do that there, the molar mass of our C3, so that would be 3 times 12.01 for our carbons. We have 8 hydrogens, each at 1.008 grams per mole. Again, this is coming from the periodic table, plus 1 times the 16 grams per mole for our oxygen. So this is basically our C3, our H8, and our O, right? Just basically where all that's coming from. And if we add all that together there, carefully, 3 times 12.01 plus 8 times 1.008 plus 16. Looks like we get like a 6009, looks like, grams per mole. Any questions on the molar mass there? Okay, now that I have the molar mass of the entire thing, and again, I do need the molar mass of the entire thing because that is really the number we're starting with. So we're starting with 72.5 grams of the entire thing here. We are going to use our molar mass as a conversion factor. Grams are up on top, so we want grams on the bottom here. So 60.09 grams per mole of the entire thing. If I stop my calculation right at this point, the grams of the entire thing would cancel. And if I were left with just units, I would have units of moles of the entire thing. Again, you could get an answer at this point, or you could continue on with the calculation. I'm going to continue on with the calculation. I don't want moles of the entire thing. I want moles of just hydrogen. So this is where our conversion factor that we got from the formula will come into play. Here, this is what's going to allow us to go from the entire thing, which we know is 1 mole of the entire thing here, gives us 8 moles of hydrogen. Again, if I stop the calculation right at this point, the moles of the entire thing would cancel, and now we would be in moles of hydrogen at this point. Any questions so far? Lastly, we're kind of close to what we want. We want moles, we have moles of hydrogen, but we're actually interested in how many atoms that would be. So that again is where Avogadro's number would come into play. That's going to allow us to now go from moles of hydrogen to atoms of hydrogen. And again, you could get an answer or continue on. Remember, setting this up in dimensional analysis way, which is where you should do it, allows you to clearly see that moles of hydrogen are up here on top, which means you should go opposite on the bottom there. And that means we should put Avogadro's number up here on top. At this point, though, when we think about the units associated with Avogadro's number, we're no longer talking about the entire sort of molecule here. We're down to just the hydrogen atoms. So the units here would become atoms at that point. The moles would cancel. We're basically, again, going to multiply everything on the top. So that's 72.5 times 1 times 8 times Avogadro's number, making sure to use that exponent. Going to hit equals. We're then going to come back and divide what's on the bottom, which looks like it is only 60.09. And that gives us 5.81, looks like, times 10 to the 24 atoms of hydrogen. Question on any part of that calculation. Does the number make sense? Well, the number does make sense. We're talking about how many individual hydrogen sort of atoms there would be in 72.5 grams. The molar mass of that guy was 60.09, and at 72.5, we have over a mole of it, which means we should have over Avogadro's numbers worth of it. And we do here, right, at 5.81 times 10 to the 24 atoms of hydrogen. Any questions on that? So that is a very common sort of question that sometimes comes up where sometimes you're not interested in sort of the entire compound or formula, stuff like that, but you're interested in one sort of part of it, maybe the hydrogen or the carbon or the oxygen. You obviously could do the same calculation for the carbon in this problem or the oxygen in this problem. The only difference would be right here. You would just substitute it out, obviously. But again, using the formula as sort of a conversion factor is a very convenient way that you could kind of go from the whole thing to each individual part. And again, we use it as a mole to mole relationship, which means, you know, you need to get everybody else into the right unit so things cancel. Any questions on any parts of that calculation there? Okay. All right, so why don't you give these guys a go here, see what you come up with. Basically the same problem. We're looking for basically how many moles and how many molecules there are in ethanol, I'm sorry. And I'll give you some numbers in case you don't have a periodic table in there yet. 12.01 grams per mole for carbon, hydrogen 1.008, and oxygen is 16. All right, take a couple minutes, see what you come up with. Basically the same problem. How many moles are there and how many molecules are there in ethanol? Take a look and see how we're doing. So we'll start with the first one. We want to know how many moles are there in 23.2 grams. So again, no real mention of atoms, molecules, or anything in the first one. So this is, again, really going from grams to moles, and our molar mass there is our sort of conversion factor to do so. Again, we get that from the periodic table. We're just going to add up all the parts of it. So in this case, we have 2 carbons at 12.01. We have 6 hydrogens at 1.008. And it looks like we've got an oxygen there at 16, which means if we add all that together there, 2 times 12.01 plus 6 times 1.008 plus 16 gives us 4607, it looks like, grams per mole. And remember, we basically can write 2 conversion factors for that. So we will start with our 23.2 grams of ethanol. Here again, dimensional analysis way is the way you should be doing this, so you can see all the units correctly cancel. Grams on top, which means grams need to go on the bottom. Again, opposites to cancel. Remember, the number always stays with the grams part, and when we do molar mass, again, it is always per 1 mole. Grams cancel, and we take 23.2 basically in this case and divide it by 4607, and that does give us a 0.504 units here would be moles of our ethanol. Any questions on the first part of the calculation there? Second part is how many molecules are there in 23.2 grams of ethanol? Again, molecules, the key word here that tells us Avogadro's number is involved. If this was the original problem, we obviously would have to do the first part here, but since we already did the first part, we could just pick it up from that point. That means we're already in moles at this point. And obviously to go from moles to molecules in this case, that is Avogadro's number, and that again is our 6.022 times 10 to the 23. Here we would use it as molecules. In 1 mole, we use it as molecules because that is a molecule. And basically, again, dimensional analysis here. Moles on the bottom so that they cancel. Avogadro's number up there on top. Again, multiplying 0.504 times Avogadro's number in this case, and basically dividing by 1, which means you don't really need to do it. Gives us, if you use the rounded number, 3.0, I guess 4 in that case, times 10 to the 23 molecules. If you don't use the rounded number, you might end up with 3.03. Any questions on grams, moles, molecules, how to solve for the whole thing, individual sort of elements? Any questions on any part of that there? Clearly, I think as I might have mentioned last time, molar mass, grams per moles, grams 2 moles, moles 2 grams. Really, the conversion factor we use a tremendous amount of chemistry. Avogadro's number does sort of creep up every so often, but nowhere near, again, sort of the conversion from grams to moles and so forth. So that's definitely one we use a lot. All right. So I think what we'll do is skip this one since we kind of did a similar one. And what we're going to talk about now is the percent composition by mass. And we sort of touched upon it the other day, sort of in lab, sort of talking about it. And really the percent composition by mass is really a percentage, basically. And it's a percentage based on really the molar mass of the compound and basically how much mass comes from each element that's sort of involved in the compound. So what we want to do is basically figure out the total mass of the element that's in the compound, really based off the chemical formula that's given to us. And we then would want to basically divide it by the mass of the entire compound and times it by 100. So as we talked about, I think the other day as well, kind of similar to what we did with like the percent water and the hydrate and stuff like that. We figure out how much mass came from the water and we divide it by the total molar mass of the compound. So if we were to look at this guy on the bottom here, our C2H6O, what we would want to do, obviously, first off, is get the molar mass of this guy by basically adding up all the parts like we did before. And as you did that there, you would end up with 4607 really grams per mole here. And we can figure out the percentage of each of these guys, the carbon, the hydrogen, and the oxygen, by really just taking each part separately. So we see from the formula there are 2 carbons. So we would take the we would take the percentage of carbon as being 2 times 12.01 grams per mole divided by the mass of the entire thing, which is 4607 grams per mole, and times it by 100%. In this particular case here, we would end up with 12.201 times 2 divided by 4607 and times it by 100. We'll end up with like 52.14% carbon. We could do the same thing for the hydrogen here. Percentage of hydrogen would be, in the formula, there are 6 hydrogens. So we would take 6 times the molar mass of hydrogen. So 6 times 1.008 divided by, again, the molar mass of the entire compound there, and times it by 100%. And at this point, that would be 6 times 1.008 divided by 46.07. Again, times it by 100, 13 in terms of the percentage of hydrogen. At this point, as I might have mentioned last time, you clearly could do the same calculation here for oxygen. And there you would take, again, in this case, we only have 1 mole of oxygen present. So that's going to be 16 grams per mole divided by 4607, which is the molar mass of the entire compound, times 100%. And that gives us 16, divided by 46.07 times 100, 34.73% made up of oxygen. What I was saying is, if you actually got these two, because carbon, hydrogen, oxygen make up 100% of all the elements present, you could have added these percentages together, then subtracted by 100 to sort of get your last percent, and then, come out pretty close with rounding and stuff like that. So that's an alternative way to get the last guy in a situation like this. What we see here is by mass, it is, about half made up of carbon, about 35% made up of oxygen by mass, and the least by mass there is our hydrogen, which obviously only weighs the lightest of all that, which is 1.008. Any questions on how to calculate percent composition by mass? So pretty straightforward. You basically just, molar mass of the entire compound, the mass of the one element that you're interested in, divided by the total mass, and times it by 100. Obviously, again, all the percentages should add up to about 100% of what is present in that sort of compound. Okay. So percent composition, not too bad. And sometimes where we see percent composition come out a lot is in a situation where we are dealing with, which we touched upon last time as well, empirical formulas and molecular formulas. So let's just talk a little bit about those guys here, and again, sort of what they are, since I didn't write on the previous one. Maybe I will use that slide there. Just scribble on. All right. So last time we talked about it, but just to, again, reiterate what the difference is, when we talk about an empirical formula, the empirical formula is really the simplest whole number ratio of what is present and as we talked about last time, the molecular formula, on the other hand, as we will also talk about here, tells you exactly what is present in terms of the atoms. So, as we talked about before, if we talked about like hydrogen peroxide, this would be the molecular formula. And in hydrogen peroxide, there is 2 hydrogens basically for every 2 oxygens. We actually can reduce this down to basically that's the same as a 2-to-2 relationship, which is the same as a 1-to-1 relationship. And that's the same as 1 hydrogen for every 1 oxygen. That would be the empirical formula. Also, again, if we had, say, C2H6 as the molecular formula, that would tell you that in this particular compound, there is 2 carbons for every 6 hydrogens present. That is a 2-to-6 ratio, which again, you can reduce down to a 1-to-3 ratio, and that would give us CH3 as its empirical formula. So again, sort of the molecular formula tells you exactly what's present. And again, the empirical formula kind of gives you the simplest ratio of the elements in terms of their atoms, what is present. Again, whole number ratio can't have like a half of, atom or something like that. So it does need to be kind of whole numbers. We also probably touched upon it last time as well. Again, sometimes, like water, this is the molecular formula. And that basically is a 2 hydrogen to 1 oxygen relationship, or a 2-to-1 relationship. And that really is as far down as you can go. So sometimes your molecular formula and your empirical formula are the same. In the case of water, it would be the same because you really can't reduce it down any further and still maintain basically whole numbers for each of those atoms that are present. Now, I also might have mentioned as well, when we talk about sort of ionic compounds and we talk about sort of balancing out the charges of the positive charge cation and the negatively charged anion, all ionic compounds are typically empirical formulas. So when we're dealing with something that's ionic, those guys are always the empirical formula. And again, that's why when we have something, say, like Al aluminum and, say, chloride here, when we put them together, the simplest way to put that together to get no charge is 1 aluminum and 3 chlorides, right? So that's the simplest way to do that. And that is the correct formula for it. That gives us a 0 charge. Could you do it by taking, say, 2 aluminums and 6 chlorides? You can, but that's not the simplest way you can do that, because that's like a 2-to-6 relationship, which is the same thing as a 1-to-3 relationship. So when we're dealing with ionic compounds, they always are basically empirical formulas, because when you put them together, if you do it correctly, and this would not be correct, by the way, if you do it correctly, it should be that simplest way to put them together, get 0, and that should always give you that empirical formula. Any questions on, again, the differences there? So what we're going to talk about now is sort of formally how to go through calculating the empirical formula. We're going to see a couple different sort of situations in terms of how to calculate the empirical formula. But let's talk about the basic steps in calculating an empirical formula. And we talked about some of these steps last time in relationship to the lab, but we're going to talk about it more here, obviously more specifically in terms of sort of book type problems and regular problems, not sort of laboratory type problems. They're very similar, except for one aspect of it. So the steps to really calculate an empirical formula, sort of our steps here, is first off, it's very common to be given the percent composition of each of the elements that are present. Now, typically what we want to do is take the percent composition like we just calculated there in that previous problem, and we want to convert them into grams. So this comes back to really a basic concept of, if you have 100% of something, right, it's often good to assume that you have 100 grams. What I mean by that is if you're told it's 50% carbon and 50% hydrogen, if you assume you have 100 grams of your substance and you're given the percent compositions, that would tell you that then you have 50 grams of carbon and 50 grams of hydrogen. So by assuming 100%, you can technically assume any number you want, but the numbers change. But by assuming that you have like 100 grams of a substance in empirical formula sort of calculations, we could very simply turn our percentages basically into grams. So they basically stay the same numbers, they just become grams. So that's a very common approach. And like I said, it's very common in empirical formula problems that you're given the percent composition of each element. Once you get everybody into grams, the next thing that you want to do is convert those grams into moles. So the next thing that you definitely want to do is take the grams, convert them over into moles. And that also is something that we've been talking about here. That is using the molar mass from the periodic table. We use our molar mass basically to do that conversion. The third thing that you want to do is once you got everybody into moles, so you'll have moles of all these elements. So for example, here we would then have moles of carbon and we would have moles of hydrogen. We would want to divide by the smallest number of moles. So we want to divide everyone by the smallest number of moles. So if you do that and you hit a whole number, then you hit a whole number. That would then be your empirical formula. Now, that's a good situation. You hit a whole number. Doesn't always happen that way, but let's talk about a couple of situations here and what we do in these situations. So first off, let's just say that we got to step number 2 here. And I had, we'll just do 2 moles of carbon and I had 4 moles of hydrogen. So if I got to step number 2 and say these were the moles that I got for each of my elements that are present, in this case, we would again want to divide by the smallest. So we would take, in this case, 2 moles. And for carbon, we would take 2 moles of carbon divided by 2 moles. That would equal 1. We would take 4 moles of hydrogen and divide it by 2 moles of carbon, and that would equal 2. Here we clearly have hit all whole numbers, and those whole numbers would represent the moles of each of those guys, and that would give us our empirical formula, which in this case would be CH2. And that would be our empirical formula. Now, not everything always turns out really kind of nice like that and everything like in that situation. So let's just say, for example, we had, after we did step number 2, let's just say for step number 2, we ended up with 2 moles of carbon, but 5 moles of hydrogen. So in this case, we would still divide by the 2. So we would take 2 moles of carbon divided by 2 moles equals 1. We then would take the 5 moles of hydrogen divided by 2, and that would equal 2.5 in that case. And that would give us an empirical formula of CH2.5. Now, 2.5 is not good because you cannot have like a half a mole of something, right? So this would not be the correct empirical formula. Because of this 2.5. So what we have to do in this case, and again, this is where it would be slightly different than what we talked about if you're doing a sort of experiment like the actual experiment we talked about last week. You know, in an experimental type situation, it's okay to probably round to the nearest whole number because it's an experiment. It's not going to be perfect and stuff like that. But typically, in most problems, textbook problems, exam problems, quiz problems, you really don't want to round to the nearest number. The only time you want to round is when it's really, really close. And we'll talk about that in just a second. But in a situation like this where we have 2.5, that 0.5 is not close enough to round to the nearest whole number. So usually what we want to do is we want to basically find a factor to multiply this empirical formula by to basically get a whole number. So you can just do trial by error. Sometimes what people do, they go, okay, I got 2.5, and if I times that by 1, that's 2.5. I take 2.5 and times that by 2, that does give me a 5. 5 is a whole number. Now, the important part is, even though 5 is the whole number, the factor by which we would want to multiply the empirical formula by is 2. So that 2 would be the factor by which we would want to multiply basically that empirical formula by. So what we do is we would take our empirical formula, our CH 2.5, and basically times the entire thing by 2, not just the 2.5. That would then give us a C2H5, and that would give us our simplest whole number ratio that's present, and this would be the correct empirical formula in this case. So, in a situation where you really don't hit a whole number, you do have to do some rounding. You shouldn't do some rounding. You need to do this sort of factoring, if you will, or figuring out what factor to multiply. What are common sort of numbers where you shouldn't round? Like we just see there, 0.5 is a common one that comes up a lot. 0.33 is another one. Maybe 0.25, maybe 0.75. These are all things that are sort of too far to round. You need to kind of come up with a sort of factor to multiply it. So when is an okay time to sort of round in a textbook type problem of an empirical formula and stuff like that? It really does need to be kind of super close. Like, the difference you're seeing is really more rounding error and stuff like that. So, if you got something like obviously 0.97 or maybe 0.98 to a number, or 0.99, those are definitely okay to round. Even if you went over the whole number, like 0.01 or 0.04 or something like that, those are also in a lot of cases okay to round. But it definitely, you get these sort of numbers, sort of like this, it's definitely not okay to round in a textbook type problem. You need to really sort of figure out that sort of factor by which to multiply everybody by. Any questions on that particular one there? Okay, so those are the basic steps. So why don't we try one here, see how you do. Where are we at there? All right, so why don't you give this one a go? We were looking for the empirical formula, so try to follow those steps. It's found to be percent composition, 24.75% potassium, looks like, 34.77% Mn, and oxygen, 40.51%. Again, in the case you know periodic table, potassium is 3910, and there's a new one, 5494, I believe. 5494 grams per mole. And we got their oxygen is 16. All right, take a few minutes. We're looking for the empirical formula. Again, follow those steps we just talked about and see what you come up with. Percent composition of each of the elements by mass. So this is a good place to easily convert those percentages into grams by just assuming that we have 100 grams. Again, you can really assume as many grams as you want. The idea of the 100 grams is it really keeps these numbers the exact same. So you don't have any changing of the numbers. The only thing that really changes is, in this case, instead of 24.75% potassium, you then have 24.75 grams of potassium. You then have 34.77 grams of Mn. And then lastly, you end up having 40.51 grams of oxygen. So again, by assuming 100 grams, keeps the numbers the same, quickly gets us out of percentages into grams. And now we can really convert into our next step, which is we have these into grams. We now want to convert them really into moles, as our little tree over here says. To do that, again, we would go to the periodic table. We would find the molar mass of each of these elements, which for potassium is 3910. For Mn, as I wrote up there, is 54.94. And our oxygen, which is 16 grams per mole of oxygen. So here we're going to convert these guys into moles. So we'll take our 24.75 divided by 3910, going to get us 0.63, I guess I'll do some rounding, 3 moles of potassium. 34.77 divided by 54.94, going to give us 0.6329 moles of Mn. And lastly, 40.51 divided by 16, 2.532 moles of oxygen. Now that we have everybody into moles, the next thing we want to do is find which one of those numbers are the smallest, and we want to divide everybody by them. So in this particular case, it looks pretty close, but I guess it is the Mn that just slightly beats everybody else out there. So the Mn here is what we would want to divide everybody by. So we would divide this guy by 0.6329. We'd also divide this guy by 0.6329. And lastly, here we would divide this guy by 0.6329. That then will give us basically 1 there for potassium. That would give us basically 1 obviously here for Mn. And that will give us 2.53 divided by 0.6329. Roughly gives us 4 here for our oxygen. At this point, we pretty much have hit all whole numbers. And because we did, that basically tells us that we have, in terms of potassium, 1 mole. In terms of Mn, 1 mole. And in terms of oxygen, 4 moles, which means our empirical formula would be KMnO4, which is potassium permanganate, and this would be the correct empirical formula. Any questions on any of those steps? Again, just kind of 3-ish basic steps. Step number 1, get them into grams. Step number 2, convert them to moles. Step number 3, divide by the smallest number of moles, gives us our whole number ratios. Again, in this case, since we did hit all whole numbers, we're good. If we didn't at this point, again, if we did not hit whole numbers, got like a, say 4.5 or 4.33 or something like that, again, we would need to find a factor to try to clear those guys out. Any questions on any of the steps of this is sort of a basic empirical formula type problem. Okay, so this is one way an empirical formula problem can be found. Another common technique for sort of determining the empirical formula within a sort of experiment is through what is sometimes referred to as combustion analysis. And combustion analysis works really well for organic type of compounds, and organic type of compounds is basically compounds that contain carbon, hydrogen, and oxygen in most cases, or in a lot of cases. So a combustion reaction usually involves an organic guy plus some oxygen is added to it and makes a combustion reaction, heat flame, but it will typically always produce CO2 and water. And in this game situation here, carbon, hydrogen, oxygen are typically sort of the guys that are contained within here. Now, in this process, as we'll kind of see a picture of in a second, when this reaction sort of takes place, they basically have an absorber there that absorbs all of the CO2. So there's something there when this reaction takes place to grab out all the CO2. They also have something there basically to grab out all of the hydrogen. And the importance of each of those things is when we think about the CO2, this is basically made up of carbon and oxygen. And out of those two elements, all of the carbon had to originally come from the organic substance. So all the carbon had to originally come from the organic substance. When we look at water, it also is made up basically of two elements, hydrogen and oxygen. And the same thing here, when we grab up all that water that came, all the hydrogen that came from that water had to originate from the actual original compound. And since we have conservation of mass and all that good stuff, we know that if we could figure out the mass of carbon that was collected, we would know how much carbon we started with. If we know how much mass of hydrogen was collected, we would know how much hydrogen we started with. So we can basically figure out the mass of the carbon from the CO2. And again, that would give us basically how much carbon we started with. We could also get the mass of the hydrogen from the water, and that would give us basically the mass of hydrogen we started with. Can we use the oxygen that we collected to figure out how much oxygen we started with? And the answer is no, we cannot use the oxygen in this part because some of the oxygen that ended up here came from the oxygen gas that was added to this reaction and not just the original oxygen that was present. So we can't directly use the oxygen that was collected in the CO2 or the H2O to figure out how much oxygen was there originally, because some of the oxygen that basically got in there came from the O2 that was added and not from the original compound. But what we do know is we can figure out the mass of the carbon and hydrogen that we started with. And if we know the mass of the original compound, which basically is made up of carbon, hydrogen, and oxygen, and we basically subtract the mass of the carbon, and then we subtract the mass of the hydrogen, that will then give us the mass of the oxygen that was there. So in this sort of problem, or in a problem like this, there's sort of kind of a pre-problem, if you will, and then a kind of post-problem, if you will, afterwards. So kind of the pre-problem, and then you can then do a regular empirical form of problem. So we're going to use really the information from the combustion analysis to help us figure out ultimately how many grams of carbon there is, how many grams of hydrogen there is, and how many grams of oxygen there was in the original sample. And then we could go through our normal empirical formula situation, convert those grams to moles, divide by the smallest, and all that kind of stuff. So let's go through this problem together so you can see, again, how it works. So here we go. So this would be a typical sort of situation or information that would be given to you. Here's sort of the setup. Again, we're shooting in some oxygen here, gas, to our sample of ethanol, which is basically made up of carbon, hydrogen, and oxygen. Is going to react with some heat, go through a combustion reaction. Again, as the sort of water comes through here, is going to be grabbed up here The CO2 comes through, is going to be grabbed up here, and we'll have some extra O2 coming out again because we added some here at the beginning. So again, we're going to be using the mass of the water collected to get us basically to the mass of hydrogen. And we're going to use the mass of the CO2 here to get us to the mass of carbon that we basically started with. And that's the information that we have here. We have 11.5 grams of ethanol, and that's basically the mass of the original substance that contains carbon, hydrogen, and oxygen. It was able to collect 22 grams of CO2 and 13.5 grams of H2O. So what we want to figure out now is just those things. We want to figure out how much carbon there was and how much hydrogen there was. So we'll start with the carbon. So we're going to figure out the mass of the carbon. And that's going to come from our CO2 that was collected. Now remember though, in this case, we collected CO2, but we're really not interested in the CO2. We're interested in just the carbon part. So we can use part of a calculation that we did earlier today to help us do that. We can see from the formula that 1 mole of CO2 gives us 1 mole of carbon. Again, also, right, 1 mole of CO2 gives us 2 moles of oxygen, but we're actually interested in the carbon relationship. So much like what we did earlier today, if you remember, we actually need to get this from grams of CO2 to moles of CO2 so that we can then use this conversion factor. So that's where we would want to start with. We want to get the molar mass of CO2. So the molar mass of CO2 is going to be 12.01 plus 2 times 16, which gives us 4401 grams per mole. And that would come from the periodic table. So starting with our 22 grams of CO2 that was collected, we could use the molar mass from the periodic table, which again is 44.01 grams per mole of CO2. Grams will cancel out. And this will give us our moles of CO2, which in this case is going to be, we'll call it 0.4999 moles of CO2. Again, here we are not interested in CO2 as a whole. We're interested in just the carbon part of it. So this is where we're going to use our formula as a conversion factor. Now that we have it in moles, we know from the actual formula that for every 1 mole of CO2, we get 1 mole of carbon. I think I could do that math there. So that is going to give me 0.4999 moles of carbon. And lastly, we are interested in how many grams of carbon that would be. Remember that now that we have converted into moles of just carbon, a very common mistake is people will use the molar mass of CO2, but we should now use just the molar mass of carbon at this point. And that is 12.01 grams per mole of carbon. And that ends up giving us finally here that approximately there was 6 grams of carbon in that CO2. That 6 grams of carbon originally came from our ethanol sample. Any questions on that calculation? We're going to basically do the exact same calculation for the water, but remember that the water now will tell us how much hydrogen there is. So from the water, we can figure out how much hydrogen. Again, for using the formula here, we see that for every 1 mole of water, we actually get 2 moles of just the hydrogen. So again, we're using our formula here as a conversion factor to go from moles of the whole thing to just moles of the hydrogen. Same thing as we did with the CO2, though, we do need to convert this into moles of water first in order to use this conversion factor. So to get the mass of hydrogen from the water, we're going to need the molar mass of water, which we've done a number of times, but it is 2 times 12.01 plus 16. And that would give us 1802 there. Grams per mole. So starting with the 13.5 grams of water that was collected, we're going to convert that 13.5 grams into moles. So we will do our 18.02 grams per mole on the bottom here. That, again, you don't necessarily have to get an answer at this point, but I will. 18.02 gets us roughly 0.7492 moles of water. Again, we're not interested in water. Water here is serving really as a source of hydrogen, right? How much hydrogen there was. So that is where we're going to use our formula to go from water to just hydrogen. So in 1 mole of water, there is actually 2 moles of hydrogen. So if I do that, we're going to times that by 2, going to give us roughly 1.4983 moles of hydrogen. And much like the carbon there, we do want to know how much mass or grams of hydrogen that would be. And if we do that, we got 12. Not 12. We want to use hydrogen here, 1.008 grams per mole of hydrogen. And that would get us 1.51, we'll call it. So 1.51 grams of hydrogen that was collected came from our original sample. And you can now see that the number that we had for our original sample, if you remember back here, was 11.5 grams of ethanol. So within that 11.5 grams, we already now know that 6 grams of it was carbon, 1.51 grams of it was hydrogen. That means whatever is left over at that point should be how many grams of oxygen there was. And that's the last thing that we're going to do here to get our numbers that we need. We're now going to use the grams of hydrogen that we collected, the grams of carbon that we collected, and the original mass there. So we know that the 11.5 grams of ethanol, which again is our carbon, hydrogen, and oxygen. We subtract out our 6 grams of carbon minus our 1.51 grams of hydrogen. That will now tell us that the mass of oxygen that's left over at this point, 11.5 minus 6 minus 1.51, would be approximately 3.99 grams of, we'll call it 3.99 grams, pretty close to 4 grams of oxygen is present. Any questions on that there? So now that we have all the grams of the 3 elements, we are ready to actually now start basically the empirical formula part of the problem. So all of this basically is to get us to a point where we can now go through our steps of our empirical formula. And that means that we're going to take these grams and convert them into moles. The good news is, since I did get a number for each of the steps that I did my calculation with, I actually have the moles of a couple of these guys. I already know that, 1.51 grams of hydrogen is that many moles. And I know that 6 grams of carbon is that many moles, which really means I just need to convert this guy into moles. So we'll copy those numbers kind of over here and see what we end up with. Hope I got a page here to write on. I think so. Yeah, perfect. So I had 0.4999 moles of carbon from the other slide there. So 0.4999 moles of carbon. I also had 1.4983 moles of hydrogen. And why I got it here, I'm going to convert this into moles on this page. So to convert my grams of oxygen into moles, I'm going to divide by 16. And that would give me 3.99 divided by 16. We'll call it 0.2494 moles of oxygen here. That way I got them all here. And 0.2494 moles of oxygen. Any question on sort of where I got those numbers from? All right. So at this point, we now have taken it from grams to moles. The next thing in finding our empirical formula is to divide by the smallest number of moles, which looks like in this case, it is going to be oxygen we're going to divide by. So that's going to be 0.2494, 0.2494, and 0.2494. That will yield us obviously a 1 for that guy. Will yield us about a 2 for that guy. And for the guy there in the middle, will yield us a 6 for that guy. Basically, we have now hit all whole numbers in this case. And since they are all whole numbers, that means that our empirical formula here would be C2, H6, and O. Any questions on any of those steps? So this is a little bit more involved sort of empirical formula problem. The deal on it is basically you're going to do all that steps there to get you to grams of everybody, and then you basically pick it up like a normal empirical formula problem. Any questions on calculating empirical formulas here? Okay, then let's talk about here how we also calculate the molecular formula. So to calculate the molecular formula, and again, the molecular formula is pretty much exactly how many atoms of each of those elements are present. You really, for the most part, need three things. You need the empirical formula. So that could either be given to you just straight up in the problem, or you might have to calculate it. Or once you have the empirical formula, the other thing you need is the molar mass of the compound, and that is usually given to you in the problem. So this guy here is usually given to you in the actual problem. So somewhere along the way in the problem, they'll say, hey, the molar mass of this compound is this, or the approximate molar mass of the compound is this. Somewhere in the problem, they'll tell you that. And lastly, you need to calculate the empirical formula. So that usually is something that you need to do. That's usually not given to you. And what you do is you take the molar mass of the compound and you divide it by the empirical formula, molar mass, and it'll give you a number. This number here, it's actually okay to round. Usually it's pretty close to a whole number. If it's not, you could round. It's usually okay for this part of it when you're doing the molecular formula. And it will give you a whole number. So let's just say you did that, and let's just say you got a 4 when you did that. And if your empirical formula was this, and you did this calculation, you got a 4, what that means is you would multiply your empirical formula by 4, and your molecular formula would be C8H16 would be your molecular formula. Or sometimes people, not too often these days, will write it like this, but that will basically give you your factor by which you multiply your empirical formula by to get down to your molecular formula. So let's take a look at one here to sort of finish up on to see how this works. So in this case, we have a sample of a compound that contains basically boron and hydrogen. 6.44 grams of boron, 1.803 grams of hydrogen. The molar mass of the compound is about 30 grams. What is the molecular formula? So here, remember, there's three things that we need. We need basically the empirical formula. We need the molar mass of the compound, and we need the molar mass of the empirical formula. We don't have it, the empirical formula. We do have the approximate molar mass of the compound, and obviously we don't have this either. So in this case, what we need to do is basically start with calculating the empirical formula. So that would be really the first thing that you would want to do in this case, because it wasn't given to you. So to get to our empirical formula, we do our same steps. We want to take whatever they give us and get them into grams. So they are already in grams. So that's good. So we have 6.444 grams of boron, and we have 1.803 grams of hydrogen. Again, to get each of these into their moles, we want to divide by the molar mass from the periodic table. So boron there is 1081. And hydrogen is 1.008. So if we do that, 6.444 divided by 10.81 gives us 0.5961 moles of boron. Take our 1.803 divided by 1.008 gives us 1.788. And we got 7 moles of hydrogen. Any questions on that so far? So here we're just going through the same process as we did earlier to calculate our empirical formula. We got it to grams. We now have our grams to moles. We're at the point where we will now divide by the smallest, which looks like it is this guy in this case. That's going to give us a 1 for the boron, and for our other guy, going to yield us about a 3. Since we hit all whole numbers here, this would be our empirical formula, which in this case would be BH3. Any questions on that part so far? That now really gives us the first thing that we need. And because we now have the first thing, we could actually get the third guy here, which is the molar mass of our empirical formula. So we will get our molar mass of this guy. And that again comes from the periodic table. So that's going to be 1081 for our 1 boron. We have 3 hydrogens at 1.008. That gets us 1081 plus 3 times 1.008 gives us 13.834 grams per mole. Now we have the third thing that we need. So now we're able to figure out what is our molecular formula sort of factor, if you will. So to do that, we take the molar mass that was given to us from the problem of the compound. We take the empirical formula's molar mass and we divide by it. And again, this should give us relative whole number in a lot of cases, should. And in this case, we're a little bit higher than 2.16. This is okay in this case, again, for the molecular formula part to round to 2 in this case. Again, you really don't want to do that when you're doing the empirical formula, but here in the molecular formula, because it should be a whole number factor, it is okay to kind of round on this particular part of it. So what does that 2 mean? That 2 is pretty much what we're going to multiply our empirical formula by to get to our molecular formula. And that means that our molecular formula would be B2H6 in this case. Any questions on any of those sort of steps? Questions on empirical formulas, molecular formulas? All right, we will lay it up right there for now, and I'll see